Okay, so the previous video we talked about basic hypothesis testing, what it is, the nuts and bolts in it, knowing about the null and the alternate hypothesis, significance level, what it means to state a claim and which one it would go with, the null or alternate, and talking about the different errors that could occur. So today we're going to get into the actual testing of a hypothesis. So specifically, we're going to talk about testing for the mean when your standard deviation for the population is known. Okay, so we're going to be able to find and interpret p-values using a z-test. So that's when the mean and the standard deviation for the population is known. Being able to figure out the critical values and rejection regions, and then being able to state some claims. So using p-values to make your decisions. So basically, we're going to talk about the significance level again. Okay, so the significance level again is that alpha, Greek letter alpha. That's basically saying, you know, this is how important it is. This is the margin that we're allowing to allow that error. So when the probability of the sample data, when the p-value is less than the significance level, we conclude there's enough evidence to assert the hypothesis is true. Okay? So we accept the alternate. So when the p-value is less than the alpha, we accept the alternate and we reject the null. Okay? So it gets very, very confusing at times. You really have to think. If the p-value is less than the significance level, we're going to reject the null and we will accept the alternate. Okay? That means the probability of it happening is less than that significance level threshold we stated. Okay, so that we're going to reject the null. So again, if p is less than or equal to the alpha, then you're rejecting the null and you're accepting the alpha or the alternate. If p is greater than alpha, then you just fail to reject the null. That doesn't mean you accept it. We never accept the null. We just fail to reject it. Okay? So keep that in mind with your wording. You're never going to accept the null. You fail to reject it. Little technical point there. Okay? So the p-value for hypothesis test is 0.0237. What's your decision when the level of significance is 5%? Well, p is less than alpha, so you are going to reject the null. You already had that typed up. Okay? In the next one, the p-value is the same, but our significance level is smaller. So now that p-value is actually bigger than our significance level. So you would fail to reject the null hypothesis. Okay? So if p-value is smaller, less than or equal to the significance level, then you reject the null. If it's not, then you fail to reject the null. Okay, finding the p-value. So you have a left-tail test or right-tail test. We've already talked about our z-scores. This is basically using that z-score chart. So if our z is 1.56 and you're in a right-tail test, you're talking about greater than that. So remember, we had to do 1 minus that. So you're basically looking for the probability again. That's what the p-value stands for. Okay? So if it's a left-tail test, well, if I was over here, well, our z-score chart, remember, is from the left. So that would be the z-score. That would be the p-value. If it's a two-tailed test, you have to double it because you have that percentage on both ends. So you have to double your probability, okay, that you find on your z-score chart. So understand that. So we're talking about areas. If it's a two-tailed test, you have two areas. So you have to double that p-value, or that probability from the z-score chart to find your total p-value. Okay, so let's look at how we do these. Find the p-value for a left-tailed hypothesis test with a standardized test statistic of negative 0.2 or negative 2.23. So this is what it looks like on the curve. Okay, so if I go to my z-score chart and I look at negative 2.23, I see that it says 0.0129, just like they gave here. So the area of this blue section is 0.0129. That is your p-value. That is the area that you are shading there. That is greater than our significance level of 1%, just by a smidgen. So you fail to reject the null hypothesis. Okay? That's it. You're finding that p-value, and you're determining whether it's greater than or less than the significance level. Let's try another one. Here we have a right-tailed test. The z-score statistic is 2.33. So if I'm looking at one of those curves and I'm only on the right side, you have to do 1 minus that chart number. So here's a picture of it. This is our critical region. Our z-score from the chart is 0.9901. So we're going to do 1 minus that. So our p-value is 0.0099. That is less than my significance level. Therefore, we are going to reject the null hypothesis. Probability of that happening is smaller than what we set as our significance level. So we would reject the null hypothesis. Okay? So it really depends on which tail you're talking about. If it's the left tail, you go to your chart, that's your p-value, you're done. If it's the right tail, you have to do 1 minus that. Okay? If it's two tails, so picture what this looks like. Our test statistic is 2.14. So when I go to 2.14 on my chart, I have the area 0.0162, but that is here. It's also here. So you have to double that. We have a total area of 0.0324, which is still less than the 5%. So you would reject the null hypothesis. Okay? So you have to think about what your total p-value is. It's the total area. All right. So here is our z-test for the single mean. And you have this formula. Remember, the standard deviation for the population, or the sample mean, is the same as this. Okay? So one formula kind of gives you the shortened version. The other one gives you the longer version. All right? So we're going to take our sample mean minus the null mean, okay, divided by the standard deviation of the population, divided by the square root of the number sample size. All right? So not too crazy hard. So here we go. Let's try. Auto racing, a pit stop is where a racing vehicle stops for new tires, fuel, repairs, and whatever. The efficiency of a pit stop crew that makes these adjustments can affect the outcome of a race. A crew claims that its mean pit stop for fuel and for new tires is less than 13 seconds. So that is its mean, or its claim. A random sample of 32 pit stops has a sample mean of 12.9 seconds. Assume the population standard deviation is 0.19 seconds. Is there enough evidence to support the claim at a 1%? Use p-value. So we have our claim written mathematically. So first we have to figure out what is our null and what is our hypothesis, alternate hypothesis. So our null is going to be the mean is greater than or equal to 13. It has to have the or equal to part in it. You can't add it to the claim. The claim says less than 13. So that's the claim. That's also going to match the alternate. And I'm going to write claim here, because that's kind of important to know which one is the claim. Okay, then we are going to identify our significance level. They told me the significance level, my alpha is 0.01. And now we need to figure out our statistic, test statistic. So our formula says we're going to take the sample mean, which is 12.9, minus the claim mean, that's what that sub-zero meant, the claim, divided by population standard deviation, divided by the square root of sample size. So our z-score is negative 2.98. We have to figure out, is this a left hand, a right hand, or a two-tailed test? Well, since it says less than, this would be a left-tailed test. So here's a picture of it. So we want the area of the left. So we need to go to our z-score chart. And negative 2.98 is 0.0014. So our p-value equals 0.0014. That's the area of that little piece of blue section. Now you need to compare the p-value to your significance level. And we're going to say p-value 0.0014 is less than our significance level, which is 0.01. Okay? So the p-value is less than our alpha. Now this again, how you word it. Since p is less than the alpha, we are going to reject the null. So you automatically come up here and you hit reject over the null. So if I'm rejecting the null, am I accepting the claim? Is there enough evidence to accept the claim? Support it? Or isn't there? Well, the claim is on the alternate. So it's not going to have rejection. It's in the good section. So we're going to say since .0014 is less than 0.05, we reject the null hypothesis. There is enough evidence to support the claim that the mean pit stop is less than 13 seconds. Notice that sentence includes what the problem was talking about. You do not just want to say, we reject the null and that's it. You need to have a sentence, words, saying whether there's enough evidence to support the claim or there's not enough evidence to support the claim, and what is the claim in words. Okay, so make sure you write that clearly. All right, so we have to go through all these steps. We have to state our claim mathematically. We have to figure out whether it's a right-tailed test, a left-tailed test, or a two-tailed test. We need to write our alternate and null hypothesis, remembering the null always has the or equal to part, the equality part to it. You should always mark which one is your claim, which one matches your claim, because that helps us with that last part. You need to figure out your significance level, figure out your statistic from your z-score formula here, or the standard statistic formula. Then go to your chart, find out what your p-value is based on which area you're looking at. Compare it to your significance level, and then state whether you're going to reject the null or fail to reject it, and then what does that mean for your claim. Okay? Let's try another one. According to a study of U.S. homes that use heating equipment, the mean indoor temperature at night during winter is 68.3 degrees Fahrenheit. You think this information is incorrect. So you randomly select 25 U.S. homes that are using heating equipment in the winter and find the mean indoor temperature at night is 67.2. So can you just say, oh, I think you're lying because mine's lower than yours? No, let's check it. So from past studies, the population standard deviation is known to be 3.5 degrees Fahrenheit and normally distributed. Is there enough evidence to support your claim at a 5% significance level? Okay, so first thing we're going to do is we are going to state the claim says the temperature is 68.3. So our null is 68.3 equals. The alternative hypothesis is it is not 68.3. So, not. This is two-tailed test. Anytime it's equal and not equal, it's a two-tailed test. Okay? So our significance level, the alpha is 0.05. And we're going to go ahead and do our test statistic. Sample mean that we found minus the claimed mean divided by population standard deviation divided by the square root of the sample size. So I get negative 1.57. So I go to my z-score, and I'm going to go to negative 1.57. And I get 0.0582. But that's the same over here, right? So if I combine those, my p-value equals 0.1164. Pretty big p-value. All right, so what does that mean? Our p-value is greater than our alpha, because this is greater than 0.05. Since it's greater than, we are going to, you know what I forgot to do? I'm going to go back up here and write my claim. The claim matches my null hypothesis. I remember to do that. So our probability of this happening is greater than 5%, so we fail to reject the null. So we fail to reject the null. That means I'm going to reject the alternate. Okay? So fail to reject the null means the claim is good. So there isn't enough evidence to support the claim. There isn't enough evidence to support the claim that the mean indoor temperature isn't. So remember, our claim was that it was not. I'm going to go back up and correct that. The claim was it was not equal to. Sorry, I had that written wrong. You're claiming that it's not equal to that when we did our test. So there isn't enough evidence to support the claim that it isn't. We're saying the claim that it is good. Okay? All right. Rejection region. So there's another way to do this without using the p-scores. First of all, let me go back real quick. Let me show you real quick how to do this with your calculator. I'm going to capture this question real quick. Put it on another slide. So if I want to put this and find my p-score with my calculator, keep in mind, can't use your calculator on the test. You're going to have to show the work of how to find that z-statistic score and all that fun stuff. But if we wanted to use our calculator, you have to identify all those things we already said. This is just going to get you your p-value. And on Math Excel, it's going to ask you to use your calculator to do this on a couple questions, so I want to make sure you know how to use it. So we are going to go to Stat, and you're going to go over to Test. And we are doing a z-test, so notice there's a t-test. That would be tomorrow's lesson. Okay, so we're using the first one, z-test. And the input, we are doing we're going to type in stats. If you had data, then you'd be typing it in your L1, L2 columns, but we're not using data, we're just typing in statistics. So the Claimed mean is 68.3. The standard deviation for the population is 3.5. The sample mean is 67.2. That's why it's real important, guys, to know what those symbols mean. And the sample size is 25. And then you have to say, you know, is it not equal to, is it less than, is it greater than? In this case, we said it's not equal to. That's determining whether it's a two-tailed test, a left tail, or a right tail. Same idea. And then just go down to calculate and hit calculate. Okay, so they give you the z-score. They give you the p-value from that z-score. Okay, so if we go back, notice it's a little bit off of what we found by hand. Because we're rounding this z-score. It's a little bit different. The calculator's getting all that nitty-gritty. So 11.64% or 0.1164 compared to 0.11608. See, it's a little different. So your Math Excel, when it says use technology, they want you to use your calculator, and it's going to be a little different if you do it by hand. Okay? So again, you're going to go to stat, test, z-score, or z-test. If I wanted to change that and say I just wanted to do less than, it will cut that p-score in half, because remember, we're doubling it if it's a two-tailed test. Notice the p is 0.058. The z-score is still the same. The z-score is still the same. Okay? So that's how you use your calculator. All right. Level of significance in the rejection region. So now this is a little bit different. Again, you have a two-tailed test, you have an upper tail test, a lower tail test, right or left tail test. But you're just going to sketch it and mark the region and the z-score. It's almost a little easier, in my opinion, to see it than just to do the p-value. But either way. So let's look at how this works. Find the critical value in rejection region for a left tail test with the alpha being 0.01. All right, so you're going to go to 1% on your standardized table. So 0.01. It's close to negative 0.233. So that's in that chart backwards. So they're saying left tail test. So you're over here. You know it's going to be in here. And negative 2.33. So anything that's in the rejection region would be that. So that shaded part is your rejection region. If it falls in there, that's not good. If it falls in the white spot, you're good. Okay? 0.05 for a right tail test. So 0.05, that would be 95%. Right tail test, we're going to be over here. So go to 0.95, and that's going to be 1.645, relates to 95% on your z-score chart. Okay? So you're looking at for point, instead of putting percent, let's do 0.95. So on your chart, 0.95. And this is the probability of it being there. Two-tailed test, 0.10. So you can just do 0.10, 10% in the negatives here. So 10% in the negatives is 5% on either side. So remember that significance level is a total of 10%. So this is 5%, this is 5%. So we already knew 5% is 1.645, and you're at negative 1.645. So So anywhere in either of those rejection regions, either below the negative or above the positive. Okay, so remember the significance level, you're going to split in half if you're looking for the rejection region. Okay, so if we are looking at rejection region again, if your Z test statistic falls in the rejection region, you reject the null hypothesis. Easy as that. If it falls in the other side, then you fail to reject the null. Easy enough. If it falls in the shaded area, bad. Reject the null. If it doesn't, then you fail to reject the null. So, employees at a construction and mining company claim that the mean salary of the company's mechanical engineer is less than that of one of its competitors, which is $88,200. So the claim is that the salary of the mechanics is less than that of the competitors. A sample of 20 of the company's mechanical engineers has a mean salary of $85,900. Assume the population standard deviation is 9,500 and the population is normally distributed. A significance level of 5%, test the employee's claim. So our alternative null here. So our null has got to be, oh no, it's greater than or equal to. They said less than up here. Okay, so our null is greater than or equal to. And our alternate is less than. So this is the claim. Okay. So we're going to do our picture. Let's write these over here. All right. Here we go. So it is a left-tailed test because we're talking about less than. Okay, so we're talking about just the left here. At 5%, we're going to go to our Z-score chart, and we're going to see that at 5%, look real quick and see what is the probability there, 0.05. This one we've used a couple times, so it's negative 1.645. That's our rejection region. Okay. So we are going to go to our Z formula. So 85,900 minus the claimed mean all over 9,500 divided by the square root of 20. I get a Z-score statistic of negative 1.08. If I put this on the number line, this guy right here is where negative 1.645 is, and this one right here is negative 1.08. So we are not in the rejection region. We're not. So we do not have enough evidence to support the employee's claim, because we're going to fail to reject. We are going to fail to reject. So we're okay with this. Fail to reject. So there's not enough evidence at 5% to support the employee's claim that the mean salary is less than. We are failing to reject. So we do not have enough evidence to support that claim. Okay? I mean, if it helps you kind of cross that. Whoops. I don't know, man. This thing is just moving around a lot. And back here. Okay? So again, it's important that you state it in words. do not have enough evidence to support the claim that the mean salary is less than $88,200. Okay? All right. Researcher claims that the mean annual cost of raising a child, this is our last example. I want you guys to try it real quick on your own for a minute. Pause if you have to. My married couple is $14,050. So that's is. We are claiming it is. So our null is going to be it equals $14,050. Our alternative is does not equal $14,050. So looking at this, this is a two-tailed test. So we have equals and non-equals. So this is our picture. Move these guys around again. Okay. Two-tailed test. All right. So at 5%, we're over here. And again, we talked about this one before. So it's negative 1.645, positive 1.645. Okay. They said the significance level is 10%, so that's 5% on either side. And then find your Z statistic. Okay, so we got negative 1.98. That is here. That's where negative 1.98 is. So it's in the rejection region. Okay? This is our claim, remember. And claim matched the null. So since it's in the rejection region, we have enough evidence to reject the null, which means we do not have enough evidence to support the claim. Okay, so I don't care how you write that. You can say there's not enough evidence to support the claim, or you can say there is enough evidence to reject the claim. Okay, we are rejecting the null. So, how you word it a little bit different, all right? Okay. So they actually asked, is there enough evidence to reject the claim? So yes, there is. There's enough evidence to reject the claim that the mean cost of raising a child is $14,050. All right. So tomorrow we're going to go into the hypothesis testing, maybe when you don't know the standard deviation for the population.